In the previous lectures, we have talked about ROS topics and how to create a publisher and subscriber in both C++ and Python. And you have done this using standard messages, the string messages of the standard MSGS package for very simple Hello World application, where we have a publisher that will send Hello World string, another subscriber that will receive the Hello World message. And ROS actually provides you the opportunity to create your own custom messages. Imagine that you'd like to create a message, a particular message with a particular type, and you want to exchange this message between different nodes. So in ROS you can do this, you can develop your own custom message, and we are going to see how we can do that. So first of all, you have to remind that every message name is composed by two parts. So the first part is the package name. So because every message will belong to a package, and also the message type, and this specifies the type of the message. And for example, we have already seen some example of messages like the standard MSGS/string. It is located in the standard MSGS package, and it has the name string. And string here, it has only one field that is called data. Also another topic that another message is the geometry MSGS twist, which is located in geometry MSGS package and has the name twist. And the twist message has linear component and angular component, which represents the linear velocity and angular velocity. Okay, so every message, as already mentioned, it has different fields, and every field would have a type. Okay, you can have field 1 of type 1 and field 2 of type 2. And as an example, we have the twist message. It has two fields, one that is linear and the second one is angular. And the type of linear and angular fields is vector 3. And vector 3, it's another ROS message type as well, and is composed by three components, X, Y, and Z. On the other hand, we have also the string message that we have used in the previous tutorial about the publisher subscriber exchanging Hello World messages. It has only one field that is called data and is of type string in ROS. Okay, this is a visualization of the twist message, because the twist message is composed of vector 3 messages, linear and angular, and vector 3 contains X component, Y component, and Z component. So X, Y, and Z, all of them are of type double, float 64. Okay, so this is the structure of the twist message. Now imagine that you would like to create your custom message. Okay, in this particular example, we would like to develop an IoT application. Let's say maybe using an Arduino sensor or any sensor. So this sensor is going to collect some weather information like temperature and humidity. And every sensor would have a name, would have a particular ID. Okay, and when the sensor gets every new reading, it will publish this reading to any subscriber node. So of course, this type of message does not exist in ROS. We don't have a standard message that has the following structure: ID, name, temperature, and humidity. But we can develop this on our own. So we would like to develop a new message that is called IoT sensor. And this IoT sensor will have four fields: ID, name, temperature, and humidity. So first of all, we can create this type of message, and then we can use the type of message to create a publisher of this message and also a subscriber of the other message. This is our objective. And of course, we can do the communication through a particular topic that we can give any name of preference. So let's go through the steps of creating a custom message in ROS. Now, you can consider the following package. So we have the ROS Essential CPP package. This is our package, which is inside the Katkin workspace. And we have a particular folder that is called MSG. So MSG, this is the folder where we need to create custom messages. If you want to create any new custom message, so you need to add it into the folder MSG. Okay, so inside this folder, you can create a new file that you can call, for example, iotsensor.msg. And this file, you can edit with, for example, gedit or any editor, and you can add the fields of your choice. So for example, here, we are going to add an ID of type int32. We will add a name that represents the name of the sensor of type string. We will add the temperature value of type float32, and we will add a humidity value of type float32 as well. Okay, now before being able to use this custom message, you need to do some tweaking inside the CMake list and also the package.xml. So the first step is to update the dependencies in CMake list.txt. Okay, every time you create a message, you need to update this. And the first update is to make sure that you have message generation into the part of find package. Now, if we open CMake list, and we will do this later when we do the demo, you will find here find package, Katkeen required components, and then you will add all the dependencies. So we have already added the dependencies, ROS CPP, ROSPy, standard MSGS when we have created the package. And if we didn't do that, you can do that manually by adding explicitly message underscore generation as a dependency for this package. And this dependency will allow you to create the custom message. Okay, after adding this dependency in the CMake list, the next step is to add the name of the file that we have added, the message file, which is called iotsensor.msg. We will add it in add underscore message files here. Okay, in this part, we have here files, and we add the name of the files. Now here, because you have only one file to add, so we will add iotsensor.msg, but if you create more than one message files, in this case, you will need to add all of them here. But of course, the dependency message generation, it's added only once because this is the library that is used to generate messages. But this actually will refer to the actual message file that you have created. Okay, and this will allow the compiler to generate the header files related to this custom message. And the third step in the dependencies is to update package.xml. Okay, and here just need to have focus about these two lines that are in pink. You have a build depend on message generation, and you have an execution depend on the message runtime. So you have to add these two lines here, which will be needed by the Katkeen compiler in order to generate the messages. So once you do that, you can generate the message. So you can go to your Katkeen workspace and just type Katkeen make, and finally you will see that you have a new message generated, which is the IoT sensor message. And then you can check that your custom message has been created. So like you do for any other message, you can do ROS MSG show IoT sensor. And here, of course, you can type just the name of the message, or you can also type ROS essential CPP / IoT sensor, which is better. So even if you don't write it and there is no confusion, it's going to automatically detect that it belongs to the ROS essential CPP package. And here it will tell you about all the fields that you have defined into your custom message, including the ID, the name, the temperature, and the humidity. So at this point in time, you have a new custom message that is called IoT sensor, that you are able to use it to create a publisher and subscriber, or any kind of communication between two nodes. And of course, this belongs to the ROS essential CPP package. In this video, I will demonstrate how to add a new custom ROS message and how to make sure that the message is effectively added and can be used by a ROS node. Let's get started. Our objective is to develop an IoT sensor custom message that contains three attributes: the ID, the name, the temperature, and the humidity. We have already presented the steps in the previous lecture, and now we start implementing them. First, let's navigate to our ROS package. So this is Katkeen Workspace, SRC, ROS Essential CPP. So this is the name of the ROS package where we're going to implement the ROS message. First, we need to create an MSG folder inside the ROS package root folder, which is this one. Make sure that the location is the ROS package folder and not any folder inside. For example, if you create the folder here or inside any of this folder, it's not going to be visible, and the MSG folder will not be recognized, and the message cannot be created. So it must be created in the ROS package folder. Then we create our ROS message. So let's create a new text file called iotsensor.msg. We create a document, iotsensor.msg, and let me open the whole project into Sublime or any editor of your choice. It can be Visual Studio Code. And now inside the MSG folder, we have IoT sensor MSG, which is now empty, and we will create our custom message. We will add the different fields to the file. So first of all, we add the ID. which is an integer, so I will choose int32. We add also the name of type string. We add the temperature of type float32. And also we will add the humidity of type float32 as well. Now the message file is created. You can refer to the documentation page wiki.ros.org/msg if you want to have more information about the different primitive types available for you to create custom ROS messages and to define the attributes of the ROS messages. In our case, we have used float32, int32, and string, but there are a bunch of different other types that can also be used. So after creating the IoT message, the next step is to update the dependencies in both package.xml and cmakelist.txt. So we can identify these two files over here. We start by package.xml, and we have to make sure that we have a build-depend message generation. It's already there. And also we have an execution-depend message runtime. So these are the two lines that are important to generate messages with ROS. We need also to update the dependencies in the CMake list. So first of all, in the find package section, we need to add message generation as a component. Then we need to add our message files, and we're going to uncomment this section here. And we will write the correct name of our message file. So our message file is called IoT sensor.msg. Okay, so this instruction will be responsible for adding this file to the ROS ecosystem. In addition, in Catkin package, we need to add another dependency, that is the message runtime. And finally, we make sure that generate message dependency standard MSGS is also activated here. Now we have done all the required configurations and we are ready to generate our message. Now we need to compile our package so that the message is generated. We open a terminal and then we go to the Catkin workspace, and then we have to compile using Catkin make. So you can see that our message is now generated, IoT sensor MSG. And if you want to make sure that the message is correctly generated, what you can do ROS MSG show IoT sensor. So here it's going to provide us all information about the IoT sensor message. It is located in the package ROS Essential CPP, and the type is IoT sensor, and this is the content. It has int32, that is the ID, string name, float temperature, and float32 for humidity. So these are the four fields that we have already defined in our IoT sensor.msg file. So at this step, we have already generated a message that can be used in the ROS ecosystem. In the next video, I'm going to demonstrate how we use this message in order to communicate between two ROS nodes. One node that is the publisher of this message, and the second node will act as a subscriber to the IoT sensor message. So let's see how it works. In this video, I will present a publisher-subscriber application that communicates between each other using the IoT sensor custom message. So first of all, I would like to highlight that there was a spelling error as the R was missing for the temperature field. I have added the R to fix the spelling error, and also I have compiled again using Catkin make to generate the correct IoT sensor message. Okay, so as I already mentioned before, we can use ROS MSG show and then IoT sensor to see the content of the message. Now we will create an application that uses the IoT sensor message. It will be very similar to the Talker listener application, with the only difference that the message that will be exchanged between the talker and the listener will be the IoT sensor message. So first, let's consider the file IoT sensor publisher.py. This is the equivalent of the talker.py application. So if you remember, in talker.py we have imported the string message. Then we created the publisher on the chatter topic, and we use the string message type. Finally, we keep sending a hello world message every 1 second. So we will do exactly the same. The only difference is that instead of publishing a string message, we're going to publish an IoT sensor message. So we will do the same. Here we're going to import the IoT sensor message from the package ROS Essentials CPP and .msg, .msgy, because the file is located into the MSG folder. This is the ROS Essentials CPP package, and this is the MSG folder where the IoT sensor MSG is located. So we import from that folder. ROS Essentials CPP, this is the name of the package, and this is the folder where the IoT sensor message type is located. And then we will create a publisher in the same way we did with the talker. So instead of using the shadow topic, I'm going to call the topic IoT sensor topic. And here we will use the message type IoT sensor. And here we define the queue size as before. Then we initialize the node. This is the name of the node, IoT sensor publisher node. And we will use the same sleep rate of 1 second. So this means we're going to send 1 message per second. And inside the while loop, we're going to define an IoT sensor object, and then we will populate with some values. So I'm going to assign an ID equal to 1. I'm going to assign a name equal to IoT parking, for example, 01. And then we'll assign some values to the temperature and to the humidity. So as you can see here, I am assigning some random values for the temperature using random.random, multiplied by some constant just to have plus minus 2. And same thing for the humidity. This is just to emulate that we receive kind of random values from a sensor node. This is just for emulation. And then I'm going to display the IoT sensor object, and finally I will publish this one. So let's try to run this example. Let me open a few terminals. First of all, we need to start ROS core. Okay, in this terminal, let me run ROS Essential CPP, and then IoT. So as you can see, I don't find any node that starts with IoT, although it was defined here in the SRC topic and IoT sensor. So the problem is that when you create a file, a Python file, by default it is not executable. So we need to make this file executable in order to be able to run it. There are different ways on how we can make it. So you can come down the file and right click on the properties, you go to the permissions, and then you click on allow executing file as a program. So in this case, you will see it's going to appear for us. So this is IoT sensor publisher. We can do also the same for subscribing the tile. I'm going to show that later. So let's start this one. So as you can see now, it's publishing the value of the ID and with some random values of the temperature and the humidity, as you can see. We can use ROS topic list here. So we will find that we have IoT sensor topic. We can use ROS node list. We will find that we have an IoT sensor publisher node, this one that we have created. We can use ROS topic echo, and then the name of the topic, that is the IoT sensor underscore topic. Okay, and you are able to listen to the topic. So now we can write a subscriber in the same way that we did for the listener in order to listen to this incoming information. We can also do ROS topic info IoT sensor topic. Okay, so it will tell us that the type is ROS Essential CPP IoT sensor. This is the type of the message. And now we have only one publisher, that is IoT sensor publisher node. Let's now create a subscriber. So the subscriber is going to be created in the same way as we did for the listener. Let me open listener.py. In listener.py, we create a subscriber object on the same topic of the talker, and then we define the type of the message. It was a string, and now in our case, it's going to become IoT sensor, and then a chatter callback. We will do the same strategy in the IoT sensor subscriber.py. So we will define a subscriber. In this case, it's going to subscribe to the same topic that was published by the IoT sensor publisher, that is called IoT sensor topic. And this is the name of the message type, so we need to import the same message type from here. And we define a callback function. I'm going to call the callback function IoT sensor callback. And in IoT sensor callback, we will receive the message, and simply we're going to print a message, the new IoT data received, %d for the ID, %s for the name, %f for the temperature, and %f for the humidity. Okay, so let's make it work. Our publisher is still publishing now. I'm going now to run our subscriber. So run ROS Essentials CPP IoT. So I only see the IoT publisher because the IoT subscriber is not made executable. So I can do the same way. I can go here and go to properties, permission, and allow executing the program, the file as a program, or otherwise we can go to the package and to the file itself / topic01, okay, IoT sensor. So we can try ls-l, so we can see this is now the green one is executable, but it's not the case for the IoT sensor subscriber.py. What we can do, we can make chmod and change the permission to 777. So it allows to read, write, and execute the file. And then we will do IoT sensor subscriber.py, and then the file becomes executable. So you can see now it's in the green color. Now I am able to execute the IoT sensor subscriber using run ROS Essentials CPP, and then IoT sensor subscriber.py. And you will see it's going to show the data that is received. So every time new IoT data received, what is published here, 2483 is published here. Okay, we can do also now ROS topic info on the topic IoT sensor topic. So we can see we have a publisher that is IoT sensor publisher node, and the subscriber that is IoT the sensor subscriber node. And you can see now we have built a complete application based on the custom ROS message that we have created, that is the IoT sensor message. And of course, you can do the same for any other type of message that you want to create. It depends on your application. So here I made a very simple and illustrative example using some IoT sensor device, but of course it can be applied to any hardware or any device that you want to get any information from it and plug it into a custom ROS message. So in the previous lecture, as already mentioned, we have talked about ROS topics. We talked about publisher and subscriber. In this lecture, we will talk about ROS services, okay, in which we have a client that sends a request and a server that will send back a response. So what is a ROS service? Basically, a ROS service contains one node that acts as a server and another node that will act as a client. Okay, and the communication paradigm here is that the client will send the request, okay, using a particular type of message, and then the server will send back a response. And the communication between the client and the server is synchronous. So what does it mean, synchronous? As we explained many times, when the client sends the request to the server, it will keep waiting. It will be blocked, waiting for the server to send back a response. So if the server doesn't send back a response for any reason, so the client is not going to process any other operation, okay, unless it receives. Or maybe you can do a timeout to stop the client from listening the response of the server. But basically, the communication here will be completely synchronous. So when to use ROS services is when you have a robot that requests a node that requests the robot to perform a specific action. Okay, for example, spawning one robot in the simulator. We are going to see this in a while using the TurtleSim simulator. Okay, so again, remind that a ROS computation graph contains different communication paradigms. ROS topics, we already covered this from all perspectives. And now we are going to cover the ROS services. And here you have the client sending a request and the server is going to send back a response. And as already mentioned, the communication will be synchronous between the server and the client. Okay, so in the case of the topic, as we already mentioned, we have a publisher that will send the messages only in one direction, from the publisher to the subscriber. Okay, however, in the service, you have bi-directional communication, where the client sends a request to the server, and then the server is going to send back a response to the client. And this doesn't actually happen in the case of the topic, because the topic you have only the publisher sending toward the subscriber. The subscriber never sent anything back to the publisher, and the publisher is not able even to receive anything from the subscriber. But in the context of a service, you have the client that first sends the request, and then the server will send back the response. So let's see this in the context of TurtleSim. We can make a small demo by running the TurtleSim simulator using ROS-Run TurtleSim node. And then, as we did for ROS topic list and for ROS node list, we have ROS service list. So ROS service list is going to give you the list of all available and running services. Okay? So basically, we are going to explore more this service that is called Spawn, which allow to create a duplicate turtle in the same TurtleSim simulator. So let's look at the information about the Spawn service, okay, using the ROS service info, like we do for the ROS node info, or also for the ROS topic info, we can do ROS service info /spawn. It will give us all the information about the service Spawn. So it will tell us that this service is provided by the node TurtleSim. It is available on the following URI, and it exchange message of type TurtleSim/spawn. And we will see that the message here, okay, is a little bit different from the message that is used in the topics. So don't forget that in the case of the service, we have a request and a response. So we will have a message for the request, and also we will have a message for the response. Now, the request message is going to contain some arguments, and the arguments of this message will be X, Y, theta, and name. So what does it do? This Spawn is going to create another turtle in the position XY with the direction theta and a name specified by the name here. I'm going to show you how we can use this service, but also, before doing that, let's look at the message itself. Like we do ROS message show for the topic, we can do ROS SRV info, TurtleSim/spawn, and here spawn is capital. This indicates the name of the package, and this indicates the type of the request response message. So spawn here, it represents the type of the request response message. So the request message is composed of 4 arguments, as you already mentioned: X, Y, theta, and name. X of type float 32, Y of type float 32, and theta the same, because all of these represent the pose of the robot in space, and string the name. So we are going to send this information to the Spawn service. It's going to create another turtle, and finally it will send back a response that is just the name of the created turtle. Okay, let's look how it works. We can call this service using the command line ROS service call, and here we specify the name of the service, that is /spawn, and spawn is lowercase. And then we need to specify 4 arguments. So don't forget, we have X, Y, theta, and name. Okay, so now we have this X and Y. Okay, X and Y. So this means we are going to create the turtle at position 7 in the X direction, and position 7 in the Y direction. So 0, it means it is looking at the 0 direction. Okay, so this is the angle 0, and the name will be called turtle2. Okay, this is the name of the following turtle. Okay, so this second turtle is created by the message or by the service spawn. Okay, because we have called the service spawn here, and the response after creating this turtle, it will send back a response, just the name of the turtle that we have created, and this name is the same as we have specified in the request. Okay, and you can see now the format of the response, just it's a string, and we return the name. Okay, so this is now an example on how we can run or call a ROS service here in order to create a new turtle. Now imagine that you would like to create a third turtle. Okay, is it the same thing? We can do the same thing. We can call the service spawn with the same 4 parameters. In this case, 5, 9. So here it will be created at 0.5, and here this is 9, and here the orientation is 45 degrees, okay, and the name will be, for example, turtle 9 here, or maybe turtle 3 it should be. Okay, this is the name of this turtle. Okay, this is just to show you an example of service, but of course, you can define your own services. I'm going to show you how to define a service in Rust, and how also to use it either in Python or in C++. So to quickly understand the concept, let's do this very simple example. I'm going to start Rust core, and then I'm going to start turtle sim node. So now, as you can see, we have only one turtle in the simulator. We can display the list of all services available for this node. So we can see now, using the command Rust service list, we are able to find all the services related to the node turtle sim. One of the services is called spawn. Spawn, it means duplicate. And this allows to create an additional turtle into the simulator. But before doing that, so we want to understand what is the structure of the service spawn. What does it expect as arguments? Because when the client sends a request to the server, it's going to send a request with some arguments, and then the server is going to send back a response. So here the request we're going to send to the server is to duplicate the turtle in the simulator. So we can use the command Rust service info and then the name of the service spawn. So you can see that here this service is provided by the node turtle sim. So we can find Rust node list. Okay, and here we have Rust out. This is the Rust core node, and turtle sim, this is the node. So this turtle sim node, it provides a service that is called spawn, and this is the URI where the service is located, the port number, and the type of the server. So this is the type of the message, turtle sim spawn. We can see the message format here. And then the arguments, so the client, when it sends a request, it must send the XY coordinates. It means where it will be located here in the simulation environment. So from here we have 0, 0 point, and this point is 5, 5. And then the orientation theta and the name. We can also check the type of the Rust service. This is the type here, turtle sim /spawn. So we can use the command Rust srv for Rust service info turtle sim spawn. And here we can find the structure of the message. And as already explained, the service consists of a request sent by the client and a response sent by the server. So we can see that the format of the service is composed of two different parts. The upper part here that contains X, Y, theta, name are the same as the arguments, and these are the arguments that the client should send in the request. And the second part here, it represents the response of the server. And here we can see that the server is going just to return the name of the robot that is created. So let's try to apply this here to create a new turtle sim in the simulator. We're going to use Rust service call, and then we're going to call the name of the service. So the service here is called spawn. And now we will provide the arguments of the request, X, Y, theta, and name. So let me create at 0.77. So remember this point is 5, 5. So 7, 7 should be somewhere here. And then this is the orientation. I will put 180. I can put 0. Okay. And finally the name, I'm going to call it T2. So you can see now we have created a new turtle in the simulator at the position 7, 7. We can do for another one. For example, I want to create it at, let's say, 5 and 9. I'm going to call it T3, and let me make it 90 degrees of orientation. And it's going to create something almost here. Okay, so you can see now, this is how the service request and response work. So you can see the response now is just the name. Okay, the name. This is the format of the response. So in the next videos, you are going to understand how we can implement a service. Now, in this demonstration, I'm showing how to use a service that already exists, but we will also demonstrate how to implement and create a new service and what are the different steps. So at this point in time, you just need to understand that a service has two different parts, a client and the server, and they exchange a message. So one message is sent by the client and the response message is sent by the service back to the client. So far we have introduced ROS services, and now we are going to apply this by creating a new ROS service for adding two integers. Okay, so like it is possible to create custom messages in ROS, it is also possible to create a custom ROS service. And here we are going to create a client-server application using ROS services, where the client is going to send two integer values to the server, and the server will send back the response. That is the sum of the two integers. Very simple. So before starting, let's see what are the steps to create a ROS service application. The first step is to define the service message or the service file, okay, which is similar to the message that we have created, the custom message that we have created in the previous lecture. But here, instead of having only one message, we are going to have two messages, one for sending the request and the second one for receiving the response by the client. The second step is to create a ROS service node, which will act as the server, okay, a ROS server node, which will act as the server. It will receive the input arguments from the client, will make the processing. In our case, it will be just the sum of two integers, and will send back the response. We will create also the ROS client node, and we will execute the service to see how it works. And finally, the service will be consumed by the client. So this is our simple application. We have add to ints server and add to ints client. And the add to ints client is going to send a message containing x and y values of type integer, and the server will make here the sum of both integers and finally send back the response to the client. Of course, here we are just sending int values and making very simple operation, that is the sum. But of course, you can change this by any other type of messages for the request. And you can do any kind of processing in the server depending on what you want to do. So for example, maybe you can send an image to a server just to process it and extract some useful information. Also, we can conceive a client-server application where a server will receive images from clients and perform some actions, for example, maybe execute some deep learning algorithms, and finally return the result, for example, detected object. You can imagine any kind of client-server application that can be implemented in ROS. So the first step is to define the service message. Again, inside our package ROS Essential CPP, we have a folder. This time is called SRV. When we wanted to create our custom message, we used the folder MSG. And now, because we want to create a new service, we will use the folder SRV. And here we create a file. We call it add to ints.srv. So what is the content of this file? Okay, it's simple. It will contain two values for the request message, A and B. Both are of type int64. And then you can see here three dots, which make the separation between the request part and the response part. So the response will be one field of type int64 that will take the sum of A plus B. So this is called the service definition. Here we provide the service definition, which represent the request message and the response message stored in a file of type .srv. We need to update the dependencies in the same way we do for messages, because at the end, a service file is similar to a message file, but it will contain two messages, one for the request and one for the response. So we need to generate these messages. And for this, we need the dependencies, message generation in build depend, and message runtime in the exec depend. Again, in the CMake list, we have to make sure that message generation is there in the same way as we did for creating a custom message, because this dependency is responsible for creating the request message and also the response message. We need also to add the .srv file, okay, in the section add underscore service underscore files. And here we can specify as many files as we have for service files. Here we have only one, that is add to ints.srv. And then we can make catkey make in our workspace directory to create the service in the same way that we did for the message. So you can see it's very similar to the way how we create a message. The only difference is that instead of making the file in MSG folder, we put it in SRV folder. And here the file itself will contain two parts, one for the request and one for the response, separated by 3 dots. Otherwise, every other thing is pretty much the same. And now after making catkey make, you will see that the message will be created in the devel folder inside include. You will have add to ints.h, add to ints request.h, and add to ints response.h. So you can see it will create you 3 files. One file that represents the service itself, one file that represents the request of the service, and another file in C++ that represents the response of the service. But you don't have to even know about these files or open them, just to tell you what happens when you make catkey make after successful creation of the service files. Now, you can verify that the service is created, okay, by typing ROS SRV show ROS essentials cpp /add to ints, and it will give you the content of the file. Okay, in this case, int64 A and B for the request and some for the response. And of course, here we can specify the package name / the type of the service. So as already mentioned in the steps, the first thing that we need to do to create a ROS service is to start by creating the service file or the messages that will be used to send the service request and the service response. And for this, we need to go to our package. So this is our package, ROS Essentials CPP. And then we need to create a folder called SRV. Okay, so we have SRC for the different source files. And SRV, it's a folder. If it is not created in your package, then you can create it by creating a new folder like this. And then you call it SRV for service. And then inside this folder, we will define the service file. So let's look at the content of the service file. Here we call the service file add to ints.srv. So observe the extension here is SRV. So in Visual Studio Code, we can go to the folder SRV, and here we click on the file that we have just shown. So as you have observed from the service description, we have a service request that contains 2 integers, A and B, or X and Y. So these are the 2 integers that will be sent from the client to the server. And here in the bottom part, we have the response of the server, which is only one value that represents the sum A and B. So this is what we call the service definition. So every service definition, it has 2 parts. One part that represents the request. It will contain all the parameters and all the arguments that the service will need to perform the service logic. And then the bottom part will represent the service response. So after the definition of the service file, we need to compile it so that to convert it into a source code for C++ and for Python. So now there are a certain number of steps that we need to follow in order to compile the service file. And of course, it has to be done only once when the service is created. So the first thing we need to do is to go to package.xml. So remember here in your package, you have 2 important files, one that is called CMake list and the other one that is called package.xml. It provides a description on the package, and here it provides all the information needed for the compilation. So we will need to modify the package.xml and also the CMake list.txt. So in package.xml, we need to add 2 lines. If it is not done, the first line that you need to add is build depend message generation, and also exec depend message runtime. So if you don't add this information here, the request message and the response message will not be generated. So these modules here are responsible for reading the service file and then converting it into a source code for C++ and for Python. And I will show you later on the source code. So this is the first thing that you need to do in package.xml. And then you have to do also further modification in cmakelist.txt. And these modifications, whatever you work with Python or you work with C++, you have to make them whenever you want to create new ROS service messages. So first of all, in find package here, you have to make sure that you have message generation module present here, because this one will be responsible for the message generation. So this is important here. And then you have to define your service file. You have to define the service file into the service section. So here we have add service files. Okay, we can write it in multiple lines to be clearer. Okay, and here you specify all the files. So you specify it one by one. And this is add to int.srv. It's the file that we are looking for here. So we add it in the cmakelist.txt to be considered for the compilation. Now we are ready to generate the source files from the service definition. So after doing that, we can go to the Catkin workspace and compile. Okay, I have the message already created. So, and now we can verify that our service source code was created. So we can go to the Catkin workspace, devel, include rosessentials.cpp, and here we can find our service file created here. So we have add to ints.h, add to ints request, and add to ints response.h. So all three different files are created for every service. So we can open the file. Okay, so this file defines the struct for the service, and it defines a request. It defines also a response here. So these files are auto-generated after the compilation, okay, and will be responsible for the execution of the service. We can also look at the two other files. So you can see here add to ints request. It defines A and B, two integers. So these are the integers that will be used to send the request. And the response file, it will contain the sum variable that will be sent back to the client. ROS also provides you a nice tool to verify that your service is working. You can use the command rossrv show and then the name of the service or the service type. So ROS provides us nice tools in order to check the services created in our workspace. We can use rossrv list. So there are a lot of commands that we can use. We can use list here, like we did with rossmsg. Okay, and here you can find all the services created in your current ROS installation, including the ones that you have defined and that were defined by the system as well. For example, we can identify here the service ROS essentials _cpp/add to ints. So now we are able to see that our service is already defined in our system. I can now have more information about the service. I can use rossrv show and then the service name that I have identified in the list. Okay, now it will give us information that our service, it has a request containing A and B, and the response that will return the sum. And by the way, we can use just the name of the service without specifying the name of the package. It will give all the packages that define the same service. So for example, we can know from here that add to int is defined in the package ROS Essentials CPP, and it is also defined in ROSPy tutorials. So if I go rosscd ROSPy tutorials, okay, there is an SRV folder. I can go to SRV, and here I will find add to int.srv. So I can look at the content, and here it is. It's the same one, okay, so you can see it is defined in this package as well. So now this is the first step, is to create the service file. Now, in this lecture, we are going to see how we can create a ROS service in Python. So let's look at the code. This code represents the script for the server in Python, for a ROS server in Python. Okay, we will go through this code step by step. So the first part of the code is importing the service request and response. Of course, as you have observed, after we have made catkin make, there are 3 files created. One for the service, add to each, one for the request, and one for the response. So basically, we need to import these 3 files. Okay, these 3 files will be available through the Python API and also will be available through the C++ API. In the Python API, you will import it from the package ROS essential cpp.srv. Okay, you import add to int, and same thing, you import add to int request, which represents the request message, and you import add to int response, which represents the response message. And of course, you need to import ROS.py, that is the Python client library for ROS. Now, the second part is to create the service. How to create a service? Okay, in the previous lecture, we talked about how to create a subscriber and how to create a publisher. We can create a new service that will represent the server that will be listening for incoming messages using the command rospy.service. And here you specify the service name. Okay, so here you have the service name. And then you have here the service type. And here you have the callback function or the handle function that will be executed automatically every time there is a new request received. Okay, because this is the server and this is the client. So the client will be sending a request, and this method is going to execute whenever there is a new message coming. It will be processed by this method. And then you have to spin. When you spin, this server is going to start and just waiting for incoming messages. It's as simple as this. Okay, so just you need to put emphasis to this code, rospy.service. Here you specify the service name, here you specify the service type, and here you specify the callback function. So 3 information you need to specify. And of course, don't forget to import add to ints, okay, in the beginning of your code. The callback function, which is the handle function that is executed every time that a message is received, it will just print the incoming values. So request.a and request.b. Why we call it .a and .b? Because in the message file, if you remember, the fields are A and B. Okay, so these are the 2 fields that we have defined in the service message. Okay, so now we are able to read the value coming from the server through request.a, and request, this is now the input to the handle function, okay, which will contain the incoming message. The incoming message will contain the value of A, will contain the value of B, and finally, we will return the response into a message of type add to int response that will contain the value needed, request.a plus request.b, which is the sum. So when the server will do return, this message will be sent back to the client and will be received by the client. Now let's look at the client. This is the script for the client. And again, let's go through the most important parts. So first of all, we need to import the same libraries, basically rospy, add to int service, the request message, and the response message. And here, we need to wait for the service to start, because maybe the client will send a request to a server that does not exist. So if the server is not awake, the client will be blocked, will be waiting until the service will be alive to be able to process the information. So before even sending any request, we need to make sure that the service is alive. So this wait for service is going to keep the client waiting until it makes sure that the service is alive. And then when the service is alive, it's going to process the other operations. It will create a service proxy, or what we call a service client, which will be responsible of sending the information to the server. So of course here the service proxy will connect to the server with name add to int. Of course this name is the same that was defined before in the server. This is the same name of the service that we have defined in the server. So this is important to use the same name, otherwise it will not be able to go for the service. And also we specify the type of the server, add to ints. So here we will call the method add to ints xy, which is this service. We will send x as the a value and y as the b value. And finally, the server will send back as a response. So we will finally print the value of response.sum, because sum, this is the field that will be received in the response. So here, just you need to carefully consider ROSPy.wait service that will make the service waiting before starting the communication between the client and the server. And also, this is the instruction on how to create a proxy. ROSPy.proxy service, add to int, this is the service name, and add to int here, this is the service type. Now, if we want to execute, okay, we can execute our server first, rosrun or ROS Essential CPP add server.py, and it's going to be ready to add two ints. It will be waiting. And then if you start the client, rosrun ROS Essential CPP add client.py 1 and 2, okay, this 1 and 2 value will be sent to the server. It will calculate the sum that is 3, and finally the sum will be sent back to the client. Let me show you this on a demo now. Now that the service file was defined, we are ready to go to define the server, which is the second step. Let's open the server file. Defining a ROS server is simple, and you can think about the ROS server is similar to a subscriber. But of course, there is a difference because a subscriber does not send anything to the publisher. However, the server is expected to send a response back to the client. So why a server is similar to the subscriber? Because as you remember, a subscriber defines what we call a callback function that is executed whenever a new message comes on the topic of interest. Also, the same thing when we define a server, we define something similar to a callback function, which is a handle function that is going to process the incoming message, formulate the response, and sends back the response to the client. So this is what we can observe. We define primary function here, which is called add to int server, which will initialize the node. So we're going to give the name add to int server for the server node. And then, and this is now the key instruction, we're going to start a service listening to incoming requests. So ROSPy.service is going to create a server that will be listening to incoming requests. And here, this is the name of the service, which is similar to the name of the topics when we use subscribe. But here we specify the name of the service. We specify the type of the message to be exchanged. And this is the type add to ints that we have already created. And as you can observe, we need to import add to ints request, and add to ints response. So remember that when we have compiled and generated the service messages in the devel folder and include, we have here generated 3 files, add to int request, and add to int response. So these are the 3 files that we need to import in order to be able to access the service and the messages defined for this service. So this is add to ints. And here, like we define the callback function in a subscriber, we define the handle function for the server, which is going to be executed anytime there is a new request coming. So this is like a new thread that is going to execute when a new request arrives to the server. So the handle method is going to perform the service requested. Okay, so it will perform the sum, and here we will just make a printing. And finally, it will return a response, add to int response. This is what we import. It will formulate a response, and the response contains only one argument, and this argument is just the sum of A and B. So you can see that we have here the parameter rec, it refers to the request, and the request, as you already know, it has 2 values, A and B, okay? So request.A plus request.B will represent the sum, and then we send back the response to the client using this statement. So this return statement, it is responsible for sending the response back to the client. On the other hand, let's open the add client.py. So same thing, we need to import the services that were created. So our program here is simple. It's going to read X and Y value from the arguments of the rosrun command line, and then we'll print the X and Y values. And finally, and now this is what is important, is going to execute a method that is called add to ints client. So this method add to ints client will be responsible for formulating the request and sending the request to the server. So the method add to ints client, it first starts by waiting for the service. So it must make sure that the service is ready to receive a request, because if the service does not exist, so there is no need to send the request. So first of all, we have to make sure that the server is awake, and the server is defined by the name of the service. Similar to the topic name, this is the service name. So first of all, we wait for the service to be available, and then we will use the method rosspy.serviceProxy. So service proxy will be responsible for sending the request to this service and specifying the type of the service, add to ints. So add to ints, it contains the information of the request, okay? So this is now the name of the client object that we have created, and from the type add to ints that already defines A and B as parameter of the request, this object is going to take as input X and Y, which are A and B that were defined in the request, okay? And this method will be responsible for connecting to the servers, sending the request by sending the values of X and Y, and then waiting for the response to come. When the response comes, so the response, as we already know, it has only one value, that is the sum. We are going to return the sum. So you can see this is now the sum that we will receive from the response. And that's pretty much it. Now we can try to run the service and the client. So in the first terminal, I'm going to run, so let me run first ROS-core. And now we can run our server first, ROS-run, ROS-essential, and add server.py, ready to add two ints, so now the server is running. And then on another terminal, I'm going to add another terminal. We will make ROS-run, ROS-essentials, add the client.py. So now when I execute add client is going, of course, I have to specify X and Y values. So let me put 2 and 8. I will send this value to the server. And finally, requesting 2 plus 8. And then I will receive a response, 2 plus 8 equal to 10. Now, if I go to the terminal of the server, okay, so returning 2 plus 8 equal 10. So the server has received X and Y values, calculate 10, and then send it back to the client. Now you know how to define a client and the server for ROS services in ROS. Okay, and just to summarize, for the server, it looks like a subscriber because we define here a server that is going to listen over a certain service name, and it will define the type of the service and also a method similar to the callback function that will handle the request and then send back the response. On the other hand, the client is going to define a method that will wait for the service to be available, and then we'll use a proxy to create an object, and this object will be used to send the request to the server and finally get the response back. This is the implementation of ROS services in Python. In the next video, I'm going to show how to implement ROS services in C++. A ROS service in C++ is also simple. In what concerns creating the service file and compiling the service files, all the operations are exactly the same as we did with the Python implementation. Now we will define two files, the server.cpp and client.cpp. Let us have a look at the add to int server.cpp file. So the application logic is the same. Here we have the main function, and first of all we initialize the node as we do with any ROS program in C++, and then we will define our service server, which is similar to a subscriber as already mentioned in the previous video. So this is now the service object, okay, which is going to advertise the service on this service name, add to ints, and also will define the method that will handle the incoming request. So this is similar to the handle method that we have defined in the Python code. We call it handle add to ints, and now we just call it add. So we can call it add handle, the same thing. And this add is going to have two parameters, one parameter that specifies the request and one parameter that specifies the response. So comparing with the Python version, here we have only the request as parameter for the handle method, and here in the server, in the C++ version, we specify the request and also the response. So when a server receives a request, is going to execute the method add and will extract the information A and B from the request. So we need to import the service file, which also refer to the service request and service response. This is why we are able to use them here, okay? And then we will calculate the sum as being equal. This is response.sum. So this is the response object. We have a pass by reference here. Response.sum is equal to the request.a. So remember that the message format of the request contains A and B. I can show you a reminder here. Those SRV show and then the service name. So you can see A and B are the two inputs for the request. This is why we have request.a and request.b. And then we calculate the sum. And finally, we will send the sum back to the client. So here the service will return a Boolean variable. When it executes correctly and sends back the response to the client, it will return true. So when it returns true, it means now it has sent the response to the client. On the other hand, this is now the file for the client. This is our main function. We first initialize our node. We read the argument from the command line, okay? And then we create a new client. So this is ROS service client. Okay, using the service client generic method of the node handle, and here we specify the type of the client. So in C++, we use generic methods to define the service client. This now specifies the type of the client and then the name of the service. So you can see there is a little bit of difference in the way how it is implemented, although the application logic is the same between C++ and Python. Okay, so in C++, we use service client generic method in order to define the client that will access the service. So now we create our service object, okay, that will contain a response and a request. So service.request.a, we're going to assign the value that we read from the command line. And here we will assign the value B to the second value that we receive from the command line. And then we will use the service client that we have created in order to call the service. So client.call, and here we will specify the service message that will be sent. So this one is the service message. It will be sent to the server, and finally we will wait for the response. So if the service call is made successfully, in this case, we can return the sum through the response message srv.response.sum. Otherwise, we are going to send a message to inform that the service call was not successful. So now this is the explanation of the C++ code, and now we need to execute it. To be able to execute the code, we need to make some modification into the CMake list. So in the CMake list.txt, we need to add the instructions to add the executable of the server and the client in the same way that we did it before for the talker node and the listener node and the robot cleaner. And this is the difference between C++ and Python. In Python, you don't need to compile and you don't need to bother yourself with CMake list, which makes Python much more simple. But also C++ has its own advantages, and sometimes it might be needed to perform some specific operations. So when you add the executable, this is the name of the server node, and this is the path to the CPP file. It is src topic1 service, and then add to ints client CPP and add to ints server.cpp. Then we need to add the target link library between the node created and Catkin libraries, and also add the dependencies. So here we need to add the dependency ROS essentials, and same thing here. Now we have everything in place to compile. So I'm going to go to Catkin workspace and then Catkin make. So you will see we will have two files to be created. You can see now it is now created. We have added two files, add to int client cpp.o and add to int server.cpp.o. So we are able now to run the service ROS run, ROS run, ROS essentials, and then the name add to ints server. So this is the name of the server node, okay? This is the server node executed in C++. Now I can go to the first one, then ROS run, ROS essentials, add two ints. This is the client, and I will specify 4 and 7. Okay, so the sum is equal to 11, and you can see here the request is x equal to 4, y equal to 7, and the response was 11. And now I have the C++ server running. I can also send the request using the Python. So let's run the request of the Python code. Add client.py. I'm going to send 3 and 9, and I will receive 12 from the server running in C++. So this is now the advantage of Rust, whatever you develop your programs in C++ or Python, they are interoperable because they exchange serialized messages. So, and they will be processed in agnostic manner, whatever it is C++ code or Python code. So in this video, I have presented how to implement a client-server application in Rust to develop Rust services. If you want to develop any other Rust service, you will need to follow exactly the same steps, starting by creating the service file that contains the request message and the response message, compile the service files, you generate the source codes for C++ and Python, then you can create your server, then create your client and execute all together.